Good morning students. So previous session we have discussed subtraction of unsigned numbers. Now this session one example I have taken subtraction of signed numbers, right. They will ask the questions subtraction of unsigned numbers as well as subtraction of signed numbers. Same steps we have to follow, but here it is included with the one more extra bit, that is nothing but the sign bit here, right. Now here I have taken subtract 32 from 64, right. So m minus n form, right. So first step is what I have to add r's complement of n with m here. Now here r's complement is what, which number system we have taken? It is the binary number system. So r's complement is nothing but what here? 2's complement. And one more extra point when you are comparing with unsigned numbers is, in case of signed numbers you have to take 8 bits here, right. So the given binary data should be in which format here? 8-bit format. So here I have what? 7 bits and here you have here 6 bits. Now you have to take what here? 8-bit format. Now in this case, so I have to add here one more extra bit at the left side 0. Now for this I have to add how many bits? 2, right? 2 zeros I have added. So both are in which format here? 8-bit format. First step is what? Finding the r's complement of n. N is nothing but what here? 32. So first I will find out what here? 1's complement of n. So this 1 1 0 1 1 1 1 1. Now I got r's 1's complement of n. Now next step is what here? 2's complement of n. Now in that case 2's complement is what? Adding at the least significant bit 1. Now 1 plus 1 0 with complement 1, 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 1 plus 1 0 with complement 1. Now 1 1 1. So this is a 2's complement of n. Now what I have to do first step? Add minute with what here? The r's complement of subtrahend. So minute is nothing but what here? 64. I should add the r's complement of the subtrahend. Subtrahend is nothing but what here? This value. Now adding this value I should add with what here? Minute. So 0 1 1 2 6 zeros here, right. So now I am adding here, right. So this is m and this is r's complement of n. So both I should do what here? Addition. Now in this case 0 0 0 0 0 1 plus 0 is what here? 1. 1 plus 1 is 0 with carry 1. Again 1 plus 1 is 0 with carry 1. Right? Same previous case also I told m is greater than n. Second step is what? First step I have done m plus r's complement of n. Now second step is what? Checking whether m is greater than or n. Now in this case m is greater than n. Now in that case see here carry is generated, right. Now after this carry bit one more bit you have to consider. This see here 1 is considered as a carry bit, right. Now 0 after that carry bit whichever bit is there that is considered as a sign bit. This is the difference mark. Previous case we did not included this sign bit, but in case of the subtraction of sign numbers you have to consider what here? Sign bit. First one is a carry bit, second one is a sign bit. Next whatever you are getting, this is nothing but the result. Result of 64 minus 32. 64 minus 32 is nothing but what again? 32. So 2 to the power of 0, 1, 2, 3, 4, 5. That is 2 to the power of 5 is again what here? 32. So you have got what here? 32. Now what is the use of this sign bit? Then sign bit is used for represent whether the result is positive or negative here. So when you are doing 64 minus 32, so you know that what? It is automatically plus 32 only. So when sign bit is 0, right, then in that case it represents positive result, right. When sign bit is 1, then it indicates what here? Negative. So that is the use of this sign bit here. So extra concept, that is nothing but the sign bit. So this we have done this concept. Now next one we have error detection codes, right. So it is very important. They will ask for 7 marks here this question. So what is the use of this error detection codes, or you can say that error detection with odd parity, right. So now in this case we have multiple number of codes, right. Here I told error detection codes. So whenever you are transmitting the data from source, S stands for what here? Sender or source. and D stands for what here? Destination. R stands for the receiver here. Whenever you are transmitting the data from source to the destination, then in that case, right? So I have sent data from source. When it is receiving at the receiver, right? So the data may be encrypted. The data may be changed here, right? So few data may be here. It is going to be lost or some error may occur here. Whatever data you are sending from source, that will not be reached by the receiver. Then in that case, right, we have two types of codes. We have what here? Two types of codes. First one is error detection code. First one is what here? Error detection codes. And second one is error correcting code, right? A number of codes exist which are used for detecting or correcting the errors during the data transmission from source to the destination here. So what are the codes? Means we have two codes here, error detection code as well as a error correcting code. So what is this error detecting code? Means it is considered as a binary code, right? Error detecting code is nothing but a binary code, right? So which is used during digital transmission from source to the destination, right? And what is the purpose of this binary code? Means it is used for detecting the errors, right? If any error is present when data is transferred from source to the destination, then how we are going to detect that error? Means by making use of this error detecting code. But this code cannot be used to correct the errors here. It is used for what? Only detecting the errors here, right? So that code is nothing but the binary code which will be attached to the data when it is transferred from source to the destination here. It is going to identify whether the error is present or not. That is the use of this error detecting code. One more we have error correcting code, right? This error correcting code, it is also considered as a binary code. Again, it is also considered as what here? Binary code, which is used for what? It is used for detecting as well as correcting the errors here. So that is the use of what here? Error detecting as well as the correcting code here. So now how we are going to detect and correcting the code? Means by making use of the best method is parity bit, right? So what is this parity bit? So parity bit is nothing but it is a single bit, right? So parity bit is nothing but what here? It is a single bit which is added, right? If I want to transfer here 3 zeros from source to the destination, then I am adding here one more bit, right? So that bit either here I can add at the starting of the data or at the ending of the data here. Parity bit is nothing but what here? Single bit which is attached to the original data. So 000 is nothing but what here? Original data. For this I am adding one more bit here. That is nothing but what here? Parity bit. Or you can say that parity bit is considered as an extra bit. It is an extra bit which is added to the data, original data, when it is transmitting from source to the destination here, right? Either I can add at the starting of the message or I can add here what? Ending of the message here. That depends upon what? How the system is designed, right? How the digital system is designed. Based on that I am going to add either at the starting of the data or the ending of the data. And why I am adding this parity bit? Means in order to make the number of ones, the number of ones as either even or odd, right? Why I am adding here? I am adding this parity bit, right? Extra bit to the original data. Either I can add at the starting of the data or at the ending of the data. So why I am adding this? In order to make the number of ones, total number of binary ones, either even or odd, right? So if the total number of ones are even, then it indicates what here? Even parity, right? By adding a parity bit to the original data, if the total number of ones becomes even number, then in that case it supports what here? Even parity. If the total number of ones becomes odd number, then in that case it supports what here? Odd parity. So example here I can give 0011, right? Now here these 3 bits are the original data. Now I am adding what here? Parity bit. So parity bit is nothing but what here? Extra bit. So after adding this parity bit, now the total number of ones, right? They have become what here? two ones are there. So 2 is nothing but what here? Even. Then it is supporting which parity? It is supporting what here? Even parity. Right? Now here odd parity. My original data is 3 zeros. Now I am adding what here? A parity bit. So single bit I am going to add here. Then in that case, if I am adding 1 here, so how many ones are there here? 1. So 1 is nothing but what here? Odd number. Then it is supporting what here? Odd parity. Right? Here one more example if I am taking. See here 3 zeros. One parity bit I am adding. Now it is what here? 0. So no parity. 0 number of the parity bit. Then it is supporting what here? Even parity. So if you are taking here again 0, 0, 0, 0. So in case of even parity, if even number of ones are there, then it will be true. It is indicated by 0. If odd number of ones are there, then it is indicated by false. Then it is indicated by 1 here. In case of odd parity, if odd number of ones are there, then it is indicated by 0, no error. If even number of ones are there, then it is indicated by error, which is represented by what here? Binary 1. So if you understand this concept, then only we can go to the actual concept, that is nothing but what here? Error detection with odd parity. Right? Here I have given, so here you have to include 5 points. Based on this diagram only, you are going to write the 5 points here. So first point from the diagram only, right? Here you have sender and here I have taken what here? Receiver, right? So from the sender, I am going to send the data to the receiver, right? So whenever you are sending the data from source to the destination, an extra bit is going to be added to the original data. So here I am taking one example here, that is nothing but 0, 0, 0. This is my original data, right? So when I am adding this original data, right? So here I have to add what here? An extra bit. Extra bit is nothing but what here? Parity bit. So in that case, it has to generate the parity here. So for that I am using what here? Parity generator. So when you are using your parity generator, so this parity generator at the sender side and parity checker at the receiver side here, right? Parity generator at the sender side and parity checker at the receiver side. So the original data along with the parity bit which is generated, that will be sent to the receiver. Second point, first point I told, source, destination, right? The data is transmitted. Parity bit is added at the starting of the message or ending of the message. Depends on what? How the system is designed. That is the first point. Second point, when I am sending the data from source to the destination, the original data along with what here? Parity bit will received by the receiver, right? Again at the receiver, what I have? Parity checker. So the parity checker will check whether the data which is transmitted from source to the destination is exactly matching. If it is not matching, whatever parity bit here it is going to adopt, so it should match with what here? Generated parity. If it is not matching, then error has occurred when it is transmitted from source to the destination. So this parity checker and parity generated, here how it is going to be generated means by making use of this XOR as well as the XNOR gates. You can consider this parity generated and parity checker as what here? They are the logical circuits which are formed with what here? XOR gates as well as the XNOR gate. Now here I told I am taking one example 0, 0, 0. If you are coming YZ, I have taken what here? 0, 0 only, right? So 0, 0 if I am taking, when I am applying to XOR gate, if you go through the logic table, truth table of the XOR gate, if both the inputs are same, then in that case the output will be what here? It will be false, right? So both the inputs are same, the output will be false. Now 0, 0, in that case what here? Will get what here? 0 only, right? Now here again X I have taken input, X is nothing but what here? 0. This 0 and here. Now when again both the inputs are what here? Same. In that case what will be the output? What will be the output? Output will be 0. Now again not operation I am performing here. Which operation? Not operation. So 0 not operation is nothing but what here? 1. So parity generated. What is the parity bit now? Parity bit is 1. Original data is what here? 3 zeros. Now parity bit is nothing but what? 1. This parity bit I can add either at the starting of the message or at the ending of the message. Now this data is transmitted from source to the destination. When you are coming to destination here, right? So suppose if it is received in the same order, right? 0, 0, 0, then no problem. See here, I should get same parity bit. Parity checker is there, no? So here I should get what here? Same parity. Then only both are matching, adopt parity as well as the generated parity. Then there is no error. If parity checker generates 0, then in that case error is encountered. Now why is it again 0, 0 I am applying, 0, 0 if I do XOR operation is 0 only. Now this bit is what here? 0. What is parity generated? 1. Then in that case what will get here? 1. When both the inputs are different, then in that case the value will be what here? High. High is nothing but what? 1. Now you check parity generated is what? 1. Now when you are checking the parity at the receiver, what is the parity? 1. So it is matching with the both the things, sender side as well as the receiver side. Then there is no error. The original data is transmitted from source to the destination. And at the end also you should get what here? 0. Why? Because odd number of ones, right? Then there is no error. No error is indicated by what here? 0. Then you can say that the data which is received by the receiver is correct. So it is not including any errors. Now when coming here, here what you got? 1. Now I am applying here 1. 0, 1. Then in that case what will be the output? Output will be high. 1 you will get. 1. Again for 1 I am applying what here? Not operation. Then what will be the output here? 0. So here I told odd parity means what? Odd number of ones are there means what? The output will be 0. 0 means no errors. And if even number of ones are there means the output will be what here? False. That is nothing but the 1 here in case of odd parity. So what I got here? The output is 0. 0 is nothing but what? Which indicates no errors, right? Which indicates the data which is sent from the sender and which is received by the receiver. So no errors are encountered in between. Suppose if you are receiving here second case 001, then in that case the case will be different. If you are taking here 0, second case I am doing here 01. So 01 means you will get what here? 1. Round up I'll write here. 01 means 1 you will get. 1 if you are taking 0 you will get here. 0 complement is what here? 1. So here 1 is nothing but what? Indicates error. 0 indicates no error. So whenever you get this 1, then in that case it represents what here? Error has encountered, and the parity bit will also change here. If I am taking 0, 1, now it will be what here? 1. So here 1 is nothing but what? So it includes error here. So thank you.